Welcome back, students. In this video segment, we will look at one section, section 4.1, applications involving right triangles. And with this section comes some good news and bad news. The good news is the lecture is very short. There's not a lot for me to do. The bad news, and it's not really that bad, it's just normal. The bad news is that this section involves a lot of time on task with homework. Applications are word problems, and word problems are very, very difficult to master. After 30 years of teaching, I still haven't mastered word problems. So that gives you an idea that you can get better at them, but they take a lot of practice. Anyway, enough of that. So let's get started. Before we look at a couple of examples of applications of word problems, let's take a look at another aspect of this section, which just involves solving right triangles. And solving right triangles, the idea is this. You're given three parts of a triangle, or certain parts of a triangle, and you're supposed to find the rest. And remember earlier in this semester, I posed a question to you, I think the first or second video lecture, in which I posed the question, given, or true or false, I think I said it true or false, given any three parts of a triangle, you can find any other part of the triangle. And the answer is false. If you're given three parts of a triangle and one of those parts is a side, then the answer would be true. So we can't solve a triangle if we're given all three angles. We need at least one side. So if I fix that true or false question and state it as true or false, if I've given three parts of a triangle, including at least one side, then I can solve the triangle. That would be true. I can completely solve the triangle if I have at least one of those pieces of information as a side. Okay, so the next thing is we have some conventions that we're going to follow. We have a convention, I guess, we're going to follow, and that is that when we're solving right triangles, we'll use the letters small b, and small c for the length of the sides, and in particular, small c will always be the hypotenuse of the triangle. So correspondingly, to label the angles, the angles corresponding to the vertices of the triangle, we'll use capital A and capital B. Well, let's go ahead and draw the triangle that I'm kind of referring to here, to illustrate this convention. So here's a right triangle. Let me get that hypotenuse drawn in here. So here's a right triangle, and we use small a and small b for the legs of the right triangle. So if this is our right triangle, we put small a and small b as the legs, and it doesn't matter whether you call, in this case, the horizontal leg A or B, and the vertical leg is A or B. That doesn't matter, but the small c is always reserved for the hypotenuse. So once we've made a decision on where we're going to put small a and small b, the vertices of the non-right triangle, of the non-right angles rather, are going to be capital A and capital B. So the angle opposite the side small a, we're going to label as capital A, and the angle opposite side small c, we label as capital B. Okay, so this is the convention that we use for this section. Okay, so we don't use capital C for the right angle because it's always a right angle. We really don't need to identify it with a letter. So why do we make this assumption? So we can write as little as possible when we pose questions. So here's what I mean. So the question would be posed like this. So for example, solve the right triangle And the way you'll be given the information for the triangle is just by stating, in this case, B equals 54 degrees. And what else? Let's see, what do we want? C, small c, to equal 15, say, feet. Okay. So here I'm given, it's going to sound like I'm misstating something. Here I'm given 3 pieces of information. And you're thinking, well, no, I'm only given 2 pieces of information. Well, what else am I given? I'm given that this is a right triangle. So it has a right angle, and so I'm also given that there's a right angle in this triangle. So I'm given 3 pieces of information. So I don't draw a triangle when I state the problem. I didn't draw a triangle when I stated the problem. There's no need. We make the assumption that if we have information given this way, that, let me draw my triangle. The legs are small a and small b. The hypotenuse is always c, so we can label the hypotenuse as c. B is 54. And it matters not at all which of the angles, non-right angles, you call 54. Suppose I call this angle down here 54. So if that's capital B, then small b needs to be the length of the leg, or the leg opposite b. So the only angle left is A, other than, of course, the right angle. And opposite that will be the leg small a. Okay, so the first thing you do is draw a triangle with the given information using the convention that we decided on earlier, and dig in. Then start trying to find the missing pieces of information. We need small a, small b, and angle A. The first attempt might take you to using the Pythagorean theorem. Well, the Pythagorean theorem won't work here. Why not? We can set up the Pythagorean theorem, a squared plus b squared equals c squared. Why can't we go any further? Well, we have too many variables in this equation. So this is a case where we can't use the geometry that we learned in algebra or in our geometry course. We have to use some trigonometry here. So I'm going to get rid of this Pythagorean theorem. Okay, and I'm going to start digging into solving the triangle using maybe some trig. I can actually use a little geometry, though. I can use a little bit from our geometry course. I can find right away one of the pieces of information without much thought at all. And which is that? That is capital A, the angle capital A. The sum of the angles in any triangle has to be 180 degrees. And 90 of it is taken up in the right angle. So the angles capital A and capital B have to add up to 90. They have to be complementary to one another. So angle capital A has to equal 90 degrees minus 54 degrees, which is 36 degrees. Okay. Now, what I would recommend you do when you do homework problems and when you do work on your exam, I recommend that when you draw the triangle write in the triangle the information that you find. But put that information, and this is just a suggestion, you don't have to do this, right? Put that information in parentheses. This indicates a couple of things to you. Okay, first, when you go back and check your work, the items that are in the parentheses are things that you have found. So the 54 and the 15 are guaranteed to be correct because those are given things. And when you come back to check, then you see that your 36 degrees is in parentheses. So I found that, so I better check to make sure that it's correct. The next reason you might want to use parentheses around the things you found is it's kind of a deep thing. Let me explain. Let me take a minute to explain. The next thing we want to try to find is either A or B, and it makes no difference. Suppose I want to hunt for, let's say, A. To find A, I'm going to use some trigonometry. I'm given A, I'm given the hypotenuse is 15. I'm looking for A. So what is the quotient of A and 15? What is A over 15? That A over 15 is adjacent over hypotenuse, or the hypotenuse looking at the angle 54. And adjacent over hypotenuse is the cosine of 54 degrees. Now I could also have done A over 15 and regarded it as opposite of 36 over hypotenuse, and that would be the sine of 36. But I want to avoid that, even though technically either is correct, and technically both equations will allow us to solve for A, but I want to avoid using the second equation. I want to avoid using 36 degrees. Why? When both of the answers should be exactly the same, why should I avoid using 36? And the reason is pretty important. You see, the 36 degrees is something that I found. And anytime I find something, I'm introducing the possibility that it could be wrong. So if 36 degrees is wrong, and I use 36 degrees to find A, then A is also going to be wrong. So here's the long story short on this. The second reason why you put parentheses around the 36 is so that you can avoid using it to find anything else. This isn't always possible. Sometimes you have to use things that you find to find other things. But you want to try to avoid using things that you found to find other things. Okay? The big reason is that you could have made a mistake. We could have made a mistake in finding that 36. So anything else we find using that 36 is going to be wrong. Okay? A little more subtle than that is if that angle A had been a decimal, I would probably round it off. And if I use that rounded off version of A to find something else, I'm going to introduce error into that next thing that I find. And every time you round something off, you introduce error into the problem. Okay, so this is all getting much too complicated. The basic idea is try to avoid using things that you found or you find to find other things. It's not always possible, but it sort of minimizes the chances of making mistakes. So once we have A over 15 equals cosine of 54, we multiply both sides by 15, and we get A equals 15 times the cosine of 54 degrees. Once we do that, all we need to do is put this into our calculator. Be careful that your calculator is in degree mode. Okay, calculator must be in degree mode here. Calculator in degree mode. And this has been a problem that I've seen really often in 30 years of teaching trig. When you're working on an exam, you're often going between problems that have angles expressed in different ways. Some of the angles are in degrees, some are in radians. If you use a calculator to solve something when your calculator's in the radian mode, and then come to a problem where the angles are measured in degrees, you've got to change your calculator to degree mode, and we don't always do that, and that automatically will lead to a wrong answer. So just make sure you realize that you're aware of the mode that your calculator is currently in. It needs to be in the degree mode. If you do this, and if you compute this, 8 times cosine of 54, you get about 8.82. Now, if there are any chemists in the crowd of video lecture viewers, if there are any chemistry students here, students of chemistry, you'll notice that I made a huge blunder in chemistry. This would be a blunder to state the answer is 8.82. And the reason for that is called significant digits or significant figures. You see, my data were given to 0 decimal places of accuracy. So technically, I need to express A without any rounding to the nearest whole number. Well, I don't want you to obsess over that. So on your homework or on your exams, I'll try to be real careful about being specific about how many decimal places I want. If I'm not, for any reason, you can shoot me an email saying, how many decimal places do you want, or you can give maybe 1 or 2 decimal places, and that'll be fine. So I just rounded to 2 decimal places, pretty much arbitrarily. So A is about 8.82 feet. Okay, I think I said, yeah, C was in feet. Okay. At this point, we could probably go to the Pythagorean theorem and find B. But you want to avoid that for the same reason I wanted to avoid using 36 degrees. Okay, so I'm going to go up to my triangle and I'm going to put in parentheses 8.82 by A to indicate that that's what I found. And you want to avoid using that to find B. It could be wrong at worst. At best, I've introduced error by rounding off to 2 decimal places. So finding B using 8.82 will only compound that error. So try to avoid using A to find B. So let's use trig to find B also. So let's do B over 15. So that's opposite of 54. Opposite over the angle 54. Opposite over hypotenuse, and that's the sine of 54. Oops, sine of 54. And I'm realizing that little OPP that I wrote for opposite probably didn't show up real well. Opposite. Okay, so opposite B is 54. B over 15 is sine of 54. Then we multiply both sides by 15. So B equals 15 times the sine of 54 degrees, and to 2 decimal places, and once again make sure your calculator's in the degree mode, 12.14 feet. Okay, and then go back to your triangle and write 12.14. Okay, so if you're taking an exam and you solve this problem, you want to come back and check, you look at the triangle, you see the things that you found, and those are the things you got to check. Okay. This is a relatively easy part of this section. The opposite of that, the opposite, and I guess that's a fancy way of saying that, or a gentle way of saying that the other part is kind of difficult for a lot of us, is solving application problems. Now, in this chapter, or for this chapter, we're gonna use problems in the problem section, obviously, for 4.1. We're also going to solve problems from a previous section in our textbook, way back in 2.3. Way back in 2.3, there were your author listed a whole bunch of word problems that were really good word problems where you use trig to solve the problems. I didn't assign those problems because I wanted to wait until you got really good with identities and stuff. So part of your homework is going to have you going back to section 2.3. So what I decided to do to finish up this short video segment is I want to do 2 problems just to get you started with the kind of the essence of the word problems in trig. So what I'm going to do is I'm going to take a second to go off camera and copy a problem from section 4.3 in your textbook. Specifically, it's on page 138, number 72. And I'll be back in about 2 seconds. So here's our first problem. Finding the distance of a ship from shore. Finding the distance of a ship from shore. So here we go. A person in a small boat offshore from a vertical cliff known to be 100 feet in height takes a sighting of the top of the cliff. If the angle of elevation is found to be 30 degrees, how far offshore is the ship? So there's our first reading through the problem. Let's digest the problem a little bit. So we're starting with we start with a cliff that's known to be 100 feet in height. Give me a second here. See if I can draw this. I would like to use some straight lines. So here we go. Here's a cliff. Bear with me here. Here's some water. Yes, we can use a little blue here. And a person in a small boat offshore from a vertical cliff. So we'll put the guy in the boat here. Okay. We'll give him a sailboat. Put a flag on it. It's going to be a short lecture, so I have to justify stretching it out a little bit here. I'm just kidding. Okay, so a person in a small boat offshore from a vertical cliff known to be 100 feet in height. So the cliff is 100 feet in height. So what's already pretty impractical about this problem? Did you catch something impractical? We have a vertical cliff. Not real often do we get cliffs that form right angles to the water. In fact, it kind of never happens. Well, we have to make certain assumptions to make the right triangle trig work out. In sections 4.2 and 4.3, we solve oblique triangles that don't necessarily have right angles. It's kind of more realistic. But here we'll assume that we have a perfect right angle that's formed by the cliff in the water. Okay, so the person is on the boat and takes a sighting of the top of the cliff. Okay, so the person takes a sighting to the top of the cliff. Let me see if I can draw without accessing the line feature. That's about right. So the person is sitting at the front, right at the front of their boat, and they're taking a sighting to the top of the cliff. And if the angle of elevation is found to be 30 degrees, do you remember what angle of elevation is? The angle of elevation, just off to the side here, the angle of elevation is the angle from the horizon upward. Okay, so this is the angle of elevation. Angle of elevation. There's a corresponding angle that occurs if you have an angle measured from the horizon downward. This is called the angle of depression. Okay, so the angle of elevation is measured off the horizon upward, angle of depression, angle measured off the horizon downward. So the angle of elevation is measured to be 30 degrees. So here's 30 degrees. So you can see if we allow the water to be the leg of the triangle, we have a right triangle formed, and that's kind of the essence of these problems. You want to try to force right triangles to be in this situation. So once we have this information, if the angle of elevation is found to be 30 degrees, how far offshore is the ship? The common mistake that students make is they'll try to measure C, the hypotenuse. The distance from the boat to the top of the cliff, that's not the distance to the shore. The shoreline is not up there. The shoreline is at the base of the cliff. So it's not C that we're after. So if I label, say, the thing we're looking for is the distance to the shore is A, then the problem becomes pretty much like the problem we just solved earlier, solving the right triangle, except we don't need the hypotenuse. All we really need is this one part. So the next thing you want to do is try to find a trig function that relates the pieces of information that are involved here. So we have in play the vertical side, the height of the cliff, the side A that we're looking for, and the angle 30. So if we consider the angle 30, opposite that would be 100, adjacent to that would be A. And what's opposite over adjacent? Opposite over adjacent is tangent. Okay. So we solve for A. To do this is a very simple matter. So we have 100 over A equals, say, tangent 30 degrees over 1, and we cross multiply. Since we have this thing called a proportion, we have two fractional expressions equal to each other. Cross multiply. That's what we can do with proportions. We can cross multiply. Two fractional expressions equal to each other means we have a proportion, and in proportion, if we have a proportion, we cross multiply and retain equality. I want to solve for A, so divide both sides by tangent 30. So A equals 100 over tangent of 30, and you simply enter this into your calculator the way you see it. If you do that, and I rounded to 1 decimal place without any rhyme or reason, we get 173.2. If you round it to 2 decimal places, it's fine. So we get about 173.2 feet. Okay. Well, to finish this video segment, I want to do one more sample problem for you. And this sample problem comes from section, I believe it's 4.1. Let me take a quick look here. Yeah, it's page 279, number 28. So give me a second and I'll write that problem out for us. So here's our problem. It's the problem is entitled Security, and it goes like this. A security camera in a neighborhood bank is mounted on a wall 9 feet above the floor. What angle of depression should be used if the camera is to be directed to a spot 6 feet above the floor and 12 feet from the wall? At first, it doesn't sound like this makes much sense, but when you start drawing a picture, it really kind of does. So let's take a look here. So here's, I'm going to get rid of the angle, get rid of the arrow on that. Here we go. Okay, so here's our situation. A security camera as a neighborhood bank is mounted on a wall 9 feet above the floor. So here's our camera. Okay. It's mounted 9 feet above the floor. Okay. What angle of depression should be used? So the angle of depression, remember, that's measured off the horizon downward. What angle of depression should be used? If the camera is to be directed to a spot 6 feet above the floor, so we want the camera to, as we see, it's being directed just in the direction of these little arrows. I want it to be directed at a point 6 feet above the floor. Why would I do 6 feet above the floor? Well, because it might hit the top of the head of a 6 foot tall person. 6 feet above the floor. 6 feet above the floor. And 12 feet from the wall, and 12 feet away from the wall. Okay, and the question is, what should the angle of depression be? Let's call that theta. Okay, well, we don't have a right triangle here, or do we? Well, it doesn't look like we have a right triangle yet, but we can certainly impose one here. Let's do that in red. I can form a right triangle by coming horizontally this way and go for the top of the guy's head up to the ceiling. There's the right angle. And the line of sight of the camera, that's the hypotenuse. So there it is. I need to find the angle theta where the right triangle pictured here, where the angle is in the right triangle. The red right triangle is kind of upside down. Let's start seeing if we get some sides to this triangle. So what's the horizontal side of this triangle? If you translate that 12 feet directly up, looks like we have 12 feet across this way. Okay. So what about this vertical portion, this vertical leg? Well, if it's 9 feet all the way up to the from the floor to the ceiling, and 6 of those feet are taken up by the person's height, then that's not to scale, but the distance that's left is 3. So I'm trying to find theta. So I'm going to use some trig here. Why? Because it's a trig course. So what trig function relates theta and 3 and 12? Theta and opposite of theta and adjacent to theta. Opposite over adjacent is tangent of theta. 3/12. Now, we're almost done, but there's a little bit of a tricky part here. We are not going to use the trig function tangent in our calculator. We use the tangent of theta if we knew what theta was. If we knew that theta was like 28 degrees, we would take tangent, push tangent 28 and enter. We're doing the inverse of that. We're looking for the angle. If we're looking for the angle, this is very important. If we're looking for an angle, we use what's called the inverse tangent, or the inverse trig function more generally. If I knew the angle, I would use the tangent. I'm doing the inverse of that, though. I don't know the angle. I'm looking for the angle. So I'm doing the inverse of using, or the opposite, not the opposite really. I want to say the inverse of using the tangent function. I want to use the inverse tangent. So theta equals the inverse tangent of 3/12. The symbol for inverse tangent is tangent to the -1. And it doesn't mean 1 over. It doesn't mean reciprocal. That little -1 in the superscript or exponent position, that often means reciprocal. It doesn't mean reciprocal here. It means inverse tangent. The inverse trig functions are on our calculators. So if you check out your calculator, let me go to blue here. If you check out your calculator has, let's say the buttons sine, cosine, and tangent. Sine, cosine, tangent. That's a pretty ugly button there for the cosine, isn't it? I guess I could clean it up just a little bit. Well, above those buttons on your calculator is printed inverse sine, not 1 over sine, that would be cosecant. Inverse cosine, not 1 over cosine or secant. And inverse that was a big mistake. And inverse tangent. Inverse tangent, not 1 over tangent. 1 over tangent would be cotangent. Okay, so these are inverse trig functions. To access the inverse trig functions, you use the second button. In your calculator, what you would do is push second tangent 3 divided by 12, and it's going to look funny because it didn't open parentheses. Your calculator opens parentheses for you, so you push the second button, the tangent button, and your calculator will open the parentheses for you. Then you push 3 divided by 12. Here, 12 has its own button here. It should be 2 separate buttons. Then you close the parentheses. Yes, there's no 12 button. And you push enter. Enter. And if your calculator is in the degree mode, and for most of the application problems, I think all of them, the angles involved are given in degrees. If you do that, you get theta is approximately, let me use the approximate equals sign, equals with a dot over it, approximately equal to 14.04 degrees is what I got. 04 degrees. So if you're looking for an angle, you use the inverse trig functions. If you know the angle, you use the trig functions. Looking for angle, use inverse trig functions. Okay, so this should get you started on homework. This is these examples, although there were very few of them, I think there are plenty to get you started. The basic theme of this section is use right triangles to solve problems. Okay, so I'm looking forward to talking with you all again soon. Go ahead and dig into homework whenever you can, as soon as you can.